Good morning, everybody.
Good morning. Can I get you to do me can I get you to upload some supplementary videos?
Sure. Anything in particular?
7.3, 7.4, and 7.5.
So from solving and the half angle formulas and stuff.
Yeah.
I also wanted to, you guys have a test scheduled the end of this week. This week might be complicated. So I thought I would move that out a little bit.
Thank you.
Just because there's a lot going on. I mean, it might be, this week might be a bigger deal for some of you and less of a deal for others, but it could be, stressful one way or the other. And I've got some time at the end for us to have some flexibility. So giving us a little more time in chapter 7, I think is a nice idea.
I appreciate it.
So let me move. Let's move that there. So I'm going to move a couple things around and show you what the calendar will look like. I suppose it doesn't matter where that is. Work with me there. There we go. And then I'll leave that there. Okay, let's see if this looks right. So I left the test information thing there. It doesn't matter. That's just I guess I could move that later. But 7.4, 7.5 moved to the end of this week. So you've got some time to play with those videos that I'll send out. We'll probably talk more about solving today and some things about 7.4, 7.5, but it's good. It's a good thing to have some time to practice. And then, oh, right, this is on student view, so you can't see the test dates. So got the test and the scratch paper for the test on Monday, and then moved back the 8 a little bit.
Is there any way for us to tell what we got for our chapter 6 test?
Yeah, somebody sent me a message that said that those were saying not available.
Yeah.
Yeah, so I fixed that this morning, but I didn't know it said that on your side.
Because mine still says not available unless you just did it.
I did it like a couple hours ago.
Yeah. I just checked mine like an hour ago and it was still not available.
Because my side shows them, but my side has always shown them. One of you guys want to check right now and let me know? Let me check those settings again. It was a new setting because, well, it was a new setting that our person who makes the shells put in. So Cade and Cynthia, yours is showing up. Okay. So if it's still not showing up, send me a message and I'll check as to why, but the default settings are now that it should show up. And sorry about that. I didn't know you guys couldn't see it.
I saw mine, so.
And if anything like that happens, it's a little weird, just let me know. Like somebody said it, that sent me a message, I think it was last night, that they're like, hey, by the way, I was like, oh, can anybody see it? I didn't know. So just let me know and I can try to fix that. So how are the solvings going in 7.3? The answer to that seems to be quietly.
Not good. That's why I asked for the supplementary for 7.3.
Okay. So let's look at some examples then. Let's start with something nice and get increasingly complicated. So let's just start with a nice, well, let's say sine 2x plus pi over 4 equals, where do we want to go here? Yeah, well, yeah, let's start super nice, 1/2. And then we'll do a cosine 1, that's a little bit more numerical. Let's say, oh, yeah, let's do it that way. 0.8x minus 1.3. And we could go plus 2 equals 0. Do I want that? No, I don't want that. Plus 0.2 equals 0. Like that. And then we'll do a tangent. Okay, so in both of these problems, our first step will always be to isolate the trig function. You could think of it kind of like you were solving, say, the square root of x plus 1, and say that was multiplied by 3 plus 8, all divided by 5 equal 9. If somebody said solve that, the first thing you would do is isolate that radical, right? You multiply both sides by the 5, then you'd subtract the 8, then you would divide off that 3, so you'd have that square root of x plus 1 isolated, and then you would use its inverse. You'd square both sides, right? You guys are all cameras off today. I can't see you guys nodding happily or shaking your heads angrily. Joy and anger are good feedbacks. So similarly, anytime we've got things like that going on in these solvings, we want to try to isolate our trig function. This one on the left, it's already isolated. The one on the right, we'd have to subtract the 0.2, but we'll do that when we handle that problem in a minute. So we're going to want to, once we have that trig function isolated, we're going to want to use our inverse function to undo that sign. So the sine inverse of 1/2, if we just went off here and asked what is the sine inverse of 1/2, visually, we should be thinking, okay, sine inverse we know is defined in the range from -pi/2 to pi/2. Now that's back to our talks on inverse functions. You guys remember those are the restrictions for sine inverse. And, you know, are you guys happy with sort of why that's the case? Do you want to or need to talk about that a bit more? If so, let me know. Allison, you highlighted. I didn't know if you were trying to talk or not.
No.
Okay. So the sine inverse is going to give us one answer in that range. And in that range, we can either check our unit circle, or if it wasn't a nice ratio, 1/2 is one of our nice standard ratios. So if it wasn't one of our nice ratios, we could ask calculator. We'll have to do that over here on the cosine problem. But since 1/2 is one of our nice ratios, we could check on our unit circle that square root of 3/2 1/2 point happens at pi/6. So our principal inverse, that is the technical term, our principal inverse for sine of 1/2 is going to be pi/6. So this side is going to become pi/6. And arguably, it would be nice if that was it. But we know there are more solutions than just that one angle within the restriction. We know that there are other angles that make sine output 1/2. And they have to live somewhere outside of the restriction. So they'll live out here somewhere. So we look, okay, we need somewhere else that sine is going to equal 1/2. Well, 1/2 is positive, and the only other place sine is positive is up in quadrant 2. So it's got to be up here in quadrant 2. There's going to be another angle that has that same height value. So that angle is going to make another set of solutions. What is that angle? That also has a y value of 1/2. Got a couple 5pi/6s flying up there. Yeah. This angle at 5pi/6, 5pi/6 is also a solution. But as we talked about last week, also anything coterminal to those two angles is also a solution. So if, for example, we went all the way around to there and we're coterminal to that dark purple angle, we'd also have a sine value of 1/2. So not only that pi/6, but that pi/6 and anything coterminal, any adding or subtracting of a full rotation. So any multiple of 2pi that we want to add or subtract, as long as what we're multiplying by is an integer, for k an integer. Same thing with the 5pi/6. It's not only that green angle at 5pi/6, but you add any rotation, and you're also going to get a solution. Again, visually, if it helps, remember we're looking at a sine curve here, and we're looking at, okay, where does that equal one half? Well, the sine curve equals 1/2 at pi over 6, at 5 pi over 6, but also at 13 pi over 6 and 17 pi over 6. Add 2 pi, add 2 pi, and you'll get another set of answers. Add 2 pi again, you'll get another set of answers. Add 2 pi again, you'll get another set of answers. Subtract 2 pi, you'll get another answer. Subtract 2 pi, you'll get another answer. So this set, or these two sets, represent all those possible solutions. Now, again, it would be great if we were done, but we haven't solved for x, right? We've solved for 2x plus pi over 4. If we want to solve for that x, we still have more algebra to do. We want to solve for that x, we got to isolate it. So we have to subtract the pi over 4 from both sides. On this side, that's going to leave our 2x. And then pi over 6 minus pi over 4. Do not fall into the temptation of asking your calculator what this is and approximate it. We need to be able to work in exact values. So your common denominators would be 12ths. So 2 pi over 12 minus 3 pi over 12 is negative pi over 12. So negative pi over 12 plus 2 pi k. Everybody happy with that?
Makes more sense.
Cade, Brianna? Yep. Brianna, let me know when you can. Still have to solve for that x, so divide by 2, divide this whole side by 2, and we're going to get our final solution of x equals pi over 2 divided by 2 is pi over 12, so negative pi over 12 plus pi k. So that's one solution set. We got the other one to go. But same thing down here. Subtract pi over 4, subtract pi over 4. If we turn this into 5 pi over 4, that's going to be 10 pi over 4 minus 3 pi over 4 is 7 pi over 12. Positive 7 pi over 12. So just going to make that into 7 pi over 12 plus 2 pi k equals 2x. And divide by the 2, divide by the 2. 7 pi over 24 plus pi k. So that's the other half of our infinite solutions. So we refer to this as our general solution. It gives all possible solutions in 2 sets. Why does this say 12? That should say 24. I apologize for that. I think I said 24, but wrote 12. So this would be considered our general solution. Happy with that so far? So one of the things we will often be asked is to solve this equation for x in some interval. So let's say we were just asked to find solutions for that x value in the interval from 0 to 2 pi. You might be tempted to say, oh, that means I don't need those coterminals. But that's actually far from the truth. If you didn't have those coterminals, you would get this answer at negative pi over 24, which is not in the interval from 0 to 2 pi. And you would get this answer at 7 pi over 24, which is in that interval, but it's only one of the 4 answers that are in that interval. And the reason is, if you remember back to graphing, if we were to graph this expression, it's got a phase shift in it with that negative pi over 4 there, and a period compression, right? So it's going to be shifted by pi over 8, half of that. So it's going to be shifted to pi over 8, and it's going to go through its oscillation in, well, 2 pi divided by the compression factor. It's going to have a period of pi. So it's going to be there by pi shifted over pi over 8 by 7 pi over 8. And then it's going to go through another oscillation by, 15 pi over 8. Right? You guys remember graphing? And it's going to keep doing that, doing that, doing that. So if we want answers for where does that equal 1/2 between 0 and 2 pi, well, 0's there, 2 pi is there. How many solutions should we have in there? We should have 4 solutions in there. Technically, it's our normal 2 solutions times our compression factor of 2. So we should expect 4 solutions here. Now I drew this graph pretty rough, but it looks like there's about 4. And indeed, we should be getting 4. And notice that phase shift of the negative pi over 8 brought the function this way by pi over 8. That's why that first solution actually ended up in the negatives. That's why this ended up being the little tiny negative pi over 24. So the phase shift can move us into and out of that interval from 0 to 2 pi. And our period change, our compression factor, can give us a bunch of extra solutions within that interval. Or it can give us less if that, if this 2 was a very small number, like this 0.8 here, could possibly push answers outside of our interval. So we can never ignore that plus 2 pi k if we've got any kind of compression factor or phase shift or anything going on, even if we only want answers within that interval from 0 to 2 pi. Fair? So what do we do to figure out what our answers are? We just make a little chart. Because our different values for k are supposed to give us different solutions. So when k is equal to, say, 0, I'm going to call these x1 and x2. When k is equal to 0, x1 will have a value and x2 will have a value. When k is equal to 1, when k is equal to 2, when k is equal to 3, we'll have different values. Fair? So for example, when k is equal to 1, this k becomes a 1. Sorry, let's start with 0. If that k is equal to 0, then our 7 pi over 24 plus pi times 0, well, that's just our 7 pi over 24. And so x1 is 7 pi over 24. And that's within our interval. So that's a solution. Fair? If we let this k equals 0, negative pi over 24 plus 0 is going to give us negative pi over 24, but negative pi over 24 is too small to be an actual solution. And we just keep going. If we let k equal 1, then 7 pi over 24, that would be 7 pi over 24 plus pi times 1, so plus pi. And you go all common denominators with it. 24 plus 7 is what, 31 pi over 24? So 31 pi over 24. And is 31 pi over 24 within the first rotation? 31 24ths is less than 2. So absolutely. So that's one of our solutions. Let k equal 1 down here. Negative pi over 24 plus pi. You can get common denominators again if you want. It's good. Common denominators are always good. That'd be 23 pi over 24. So 23 pi over 24. That's another solution. When we let k equal 2, we'd be adding 2 pi. Does it make sense that anything positive plus 2 pi is going to be bigger than 2 pi? So that's going to be too big. It would technically be what, 55 pi over 24? And 55 pi over 24 is bigger than 48 pi over 24. So that's too big. But if we add a 2 pi there, we're going to add another 24. So that's going to be 48. So that would be 47 pi over 24. That's almost 2 pi, not close, not quite, but close. And you remember on our diagram, it looked like that last one was really close, right? And that's it being really close. If we added any more, it would again get too big. Always consider that these k's can be negative. But if we subtracted 24 pi over 24, we'd get negative. This is already negative. So the negatives are too small in both directions. So those are our answers. Those 4 values are the 4 values for x within our interval. So there's 7 pi over 24, 23 pi over 24. They don't have to be in order, but it's a good habit. And I think the computer actually asks for them in order. Just makes it easier for the computer. So within the interval, that would be your set of solutions. Now, does that all seem sensible?
Yes.
Does it require a fair amount of practice?
Yes.
Absolutely. There's a lot to keep track of there. Particularly, this second solution tends to be the big issue. Making sure you're comfortable with why there's a second set and finding that second set. Because where that second set is depends on the trig function we're talking about. You'll see when we switch over to talking about cosine, it's going to seem a little different, and it should, because we're working with a different function. But we'll talk about that in a second. Questions about this process? If you're curious about, where does this process come up? Well, if you're thinking about almost anything that's oscillating, if this oscillation is, say, a tide or some rotating engine, or toxicity toxicity levels in the blood, whatever it happens to be, when is that going to be at, let's say that's 50%, one half, say that's a 50%. When does that toxicity level reach 50% of the lethal level? I don't know, I'm just making stuff up, right? Well, that's going to happen at any of these time periods is when that's going to change. Or when at the end, we talk about polar graphing, we're going to get some neat curves that start happening. And, when does this, they tend to look, we'll get some neat curves that we'll learn how to graph. And when those intersect other things, well, they intersect other things multiple times and over and over and over again as we rotate. Imagine, one flywheel or one pulley moving around another. When do things line up? If you've ever built engines, imagine a distributor cap is big on this, making sure it's hitting those contact points at the right times over and over again. So there's, lots of nice applications on, well, why do we care about these multiple solutions? Because if we're using the trig to model something, we're modeling something that's got periodic behavior. So the idea that any solution is just going to come up once, sometimes, yeah, all you want is that one solution. When is the asteroid going to hit the planet? Well, after the first time, you don't care anymore. But when is this asteroid going to get close enough for us to see it? Well, that's going to happen over and over again during its orbit, right? So we want to be able to plot out, well, when's it going to happen? Well, when's it going to happen next? Well, when's the next time after that it's going to happen? Fair? So questions about that process of finding all these solutions before we mess with it a little bit, talk about cosine. So hopefully you're seeing the connection between the solving and the graphing. And you remember when we solved when we graphed sine, and then we went to graphing cosine, the process was basically the same, just shifted, right? So our process for solving for cosine is going to be pretty much the same, except it's going to be shifted a bit, but pretty much the same process. So the big difference between these two problems is that this first one was set equal to one of our standard angles, and the pi/4 and the 2 in that phase shift and compression factor were nice whole numbers. So we were able to get nice exact values here. Fair? The big thing that's going to make this one different is they're decimals. They're not our nice standard angles and not our nice standard fractions. So we're not going to be able to get nice exact values at the end. We're going to be approximating along the way. Fair? So that's not happening because it's cosine. That's happening because of the decimals. Fair? So make sure there's two changes here. One, it's not exact. Two, it's cosine. And those cause different effects. But just like the other one, the first thing we're going to want to do is solve this or set this equal to our trig function. So we're going to isolate that trigonometric piece. So -0.2. But as soon as we do that, how do we get rid of the cosine? We use its inverse. So again, I'm going to go off here and look at that cosine inverse of -0.2. And start by finding out what that principal inverse is. Now, because that's not one of our standard ratios, that's not 1/2 or √2/2 or the square root of 3/2 or 1 or 0. So it's not one of the ratios that come up on our unit circle. So we're not going to be able to do this exact. As soon as we recognize that, we grab the calculator. Fair? So we need the cosine inverse of -0.2. So find that. You guys have your calculators. I found sine inverse, not cosine inverse. I'm going to round to 2 decimal places just because I want to. So anybody want to suggest what they got for the cosine inverse of -0.2? Anybody want to argue with that or confirm that?
I got something different. I got like 101.54.
Okay,
Or am
why?
I don't know.
Why the different answers?
I don't know. So we're plugging in the cosine inverse of -0.2, right?
Let me stress that you're not actually wrong. Why would the answers be different?
I don't know.
You are 101 degrees,
Mm-hmm.
and Cynthia said 1.77 radians.
Mm-hmm.
So those are actually the same measure. Fair?
Yes.
But does this problem have to be in radians or in degrees? Often for the inverses, it's up to you, right?
Mm-hmm.
But this 1.3, that's part of our angle measure, right?
Yeah.
So that 1.3, is that 1.3 in radians or in degrees?
In radian.
It is in radians. How do we know it's in radians?
I don't know.
You might think you know it's in radians because it seems more like a radian scale number.
Yeah.
But 1.3 degrees is okay. It would have to have the degree symbol on it.
Oh, okay.
And that's why I was saying before, if we don't write the degree symbol, it's radians.
It's radians. Okay.
So even if this said, say, 35, is that 35 degrees or 35 radians?
It would be radians because it doesn't have the degrees symbol.
Absolutely. A fun thing to do if you're trying to mess with students, go back over to this first problem, is put things like pi over 4 degrees. Just to be, a jerk. It says degrees, when it's pi over, doesn't matter.
Yeah.
That is 3.14 divided by 4 degrees.
Degrees. Okay.
And I'm a jerk, but it's fun. So do be careful about that. If there wasn't a phase shift on this, then you could do it either way. What was it? 1.3, 1.3. If there wasn't a phase shift on there, you could do it in degrees, you could do it in radians, it wouldn't matter. You'd have to make sure you're doing the whole problem in degrees or the whole problem in radians. Fair?
Yes.
Okay, so 1.77. And again, just like we did over here, and I recommend you do this every time you do one of these, draw that out. 1.77 is nicely in quadrant 2. Did we expect that to be in quadrant 2? I mean, the cosine is negative, right? What quadrants is cosine negative in? 2 and Beatrice, Allison, Brianna, Cade. 2 and
3.
3. So in quadrant 2 and 3, so we knew our principal one had to be in 2 because the inverse is defined between 0 and pi. The other one, though, you're absolutely right, has to be down in 3.
How do you know that 1.77 goes there?
Well, if it's in radians, well, there's a couple different reasons. One, the ratio here is negative, right?
Yeah.
And cosine is negative only in quadrants 2 and quadrants 3, right?
Yes.
And the inverse is only defined between 0 and pi, right?
Okay.
So the inverse is only defined in 1 and 2. So the only places those overlap is quadrant 2. The only place cosine is negative and the inverse is defined is in the second quadrant. Fair? So even if we had no idea where 1.77 was supposed to be kind of visually, we would know it has to be in quadrant 2. And that's one of the reasons it's important for us to know both where are those restrictions. Cosine is between 0 and pi, sine and tangent are from negative pi over 2 to pi over 2. It's important to know those restrictions. And it's important for us to know what quadrants our trig functions are positive and negative in, because it all starts to work together to tell us where we are. Fair? So that's the first reason. The second reason, that is pi over 2, right? And half of pi is 1.57. So it's 3.14 divided by 2 is about 1.57. And that's more than 1.57 without being more than 3.14. mean, frankly, it's probably quite a bit steeper than that if you were to draw it in scale. And thirdly, you said it was 101 degrees, and 101 degrees is in that particular quadrant. But I wouldn't want that to be the reason why we do it. All that fair? Allison?
I have no idea.
Had you asked that question?
Yeah.
So are you comfortable with, we talked about it over here, but are you comfortable with the restrictions for the inverse functions?
Yeah.
Okay, so you're happy with cosine being restricted from 0 to pi, right?
Yes.
And you certainly know that cosine is negative in quadrant 2, right?
Yes.
So you asked, how do we know that the 1.77 is there? That's how, that combination of information says it has to be in quadrant 2. Exactly where it is in quadrant 2, it's just a diagram. I don't know where exactly it is in quadrant 2.
Why? Because you are in pain.
Is that fair?
Yes.
Okay. So one of our answers, or principal answer, will be that 1.77, so equals 1.77. And of course, everything co-terminal to it. So again, because we're in radians, it's a plus any multiple of 2 pi. And you said it was also negative in quadrant 3. So the other answer is going to be down there. Now, again, for the scale of the diagram, all we know is that these should be symmetric. So how would we find that gray angle? This is usually the one that bugs people. Add pi over 2 to the 1.77. That's an assumption that these are a right angle, which is not necessarily true, and frankly, in this case, not true. It kind of looks like it, but you can imagine if this was, steeper, that would be steeper, right? And that wouldn't be pi over 2. If that was shallower, this would be shallower, and that angle wouldn't be pi over 2. How about this? Let's think in degrees for a minute here. Let's say we were doing this at 100 degrees. What would that corresponding angle be such that those lengths were the same, such that these angles match? Now, if this is 100 degrees, what's that?
100, right?
That's also 100 degrees.
Yes.
So we actually have two choices. We could call this angle negative 100 degrees, and that would be perfectly reasonable. If this is 1.77, What's that got to be? Well, how about negative 1.77? Negative 1.77. Actually, one of the nice things about cosine. But say we didn't want to do that because we had some prejudice against negative numbers. By the way, you shouldn't have a prejudice against negative numbers. But if you did, if that's negative 1.77, well, how might you figure out this gray angle? Well, it's going to be 2 pi minus the 1.77. Fair? 2 pi minus the 1.77. Does that seem reasonable? That's one of the reasons I say draw that diagram. Trying to kind of figure out in your head where everything has to be is difficult and a lot of work. Drawing it out can help quite a bit. Again, I got 4.51 plus 2 pi k. This does end up being a nice generality though. Here, we took the angle and so took pi minus that angle, right? Here, we're taking 2 pi minus that angle. That does end up being a fairly good generality, but making sure you've got your diagram to make sure that that's working out is fairly important. Again, finding that second angle is usually what takes the most practice. But I got to send you guys off, so let's finish this problem up real quick. The rest of it is just solving for that x. So we're going to add the 1.3, add the 1.3. 0.8x equals, what's that going to be, 2 or 3.07 plus 2 pi k. Divide by 0.8, divide all that by 0.8, and whatever 3.07 divided by 0.8 is. .84. Pi over 2 divided by 0.8, or 2 pi. .85. So that's one solution set. And same thing for the other one. 6.21 plus 2 pi k. Divide by your 0.8, divide everything by your 0.8. And 6.21. 776 plus the 7.85 k. So it does feel a bit different when you're using raw decimals and approximations than when you're dealing with exact values. I'm not sure if one of them is easier or harder. They're just, I think they're just a bit different, depends on what you're used to and what you like. Dealing with sine and cosine, they're again not all that different. I think finding that second angle for cosine is a little bit harder. I think it's just a little bit harder to visualize, but once you get practice with it, it tends to go smoothly. But make sure you're, the big thing is to, once you get real comfortable with the one, finding the second angle for sine, the tendency is to want to use that same thought process for getting the second angle for cosine, and they are different. So making sure you separate those. And for me, drawing that diagram and making sure you know what quadrant you're shooting for, I think makes a big, big difference. If you can draw that diagram and know where you're looking, even if you do the wrong thing, you'll look at it and go, that's not the right place. Oh, right, I have to do it this way instead. Questions?
That makes more sense.
These do take a fair amount of practice.
I have a question. Where did you get the 7.85? I'm probably not seeing it, but
Oh, I'm taking the 2 pi divided by 0.8.
oh, okay. Makes sense. All right, thank you.
Always feels a little bit weird, the fact
Yeah.
that we're adding only to this term, but we're dividing into both.
Yeah.
And
Okay.
technically you guys are used to that. If you had, say, 2y equals 3x minus 4, or say plus 1, if you added 1 to both sides of this, you'd only add that 1 to the constant, right?
Mm-hmm.
There's no x in it. Here there's no k, so it's not a like term with that k. Fair? And then when you divide the 2, you would divide the 2 by everything, right?
Yep.
It just looks a little weirder up here with the k's, and it's just
Yeah.
Yeah.
Okay, makes sense now. All right.
And that's one of those things that you guys know that, but it just feels a little bit weird. It looks a little bit different. It takes a little bit of practice. But once you get used to it, you're like, oh, okay. But it takes a little bit.
Mm-hmm. Okay. All right. Thank you.
For sure. One of the things I recommend, your homework doesn't have a lot of these on it. And this does take practice, and it does help to have some repetition with it. So going into your textbook and some of the smaller problems at the beginning of your homework section in your textbook, and just playing with some, getting some of that repetition in there. I don't tend to push a lot of just do a bunch of problems over and over and over again, because it generally doesn't help understanding, but it does help pattern recognition. And this is a good section for some, kind of muscle memory, pattern recognition practice. So going through small problems and just kind of doing half a dozen or dozen of them just to get that pattern down and that logic down can be really helpful. So I encourage you to do that. Anything else I can do for you before I send you off today?
I had a question.
Shoot.
What if the sine and cosines were something different, like secant or something like that?
Well, tangent we'll talk about. Tangent's actually easier. I'll send out those videos for you and do tangent. But the nice thing about secant and cosecant is we don't do them. Say you had cosecant of 2x equals, even if it was something like 1.3, you could be given this problem, certainly.
Mm-hmm.
But don't do it this way. You know that cosecant is the same as sine, where the ratio is inverted, right?
Okay, that makes more sense.
So that's why we don't do it. It happens, but we don't solve it that way. Cool?
Yeah.
Cool.
I have another question.
Shoot.
So on the example you were giving, when we were solving for the second angle,
Mm-hmm.
which you were trying to do the plus, subtracting 1.3, and then to adding 1.3 to both sides.
Yeah.
Where did the 1.7 come from?
That one, the 1.77.
No, the what at the bottom, the next when you were selling for the next one.
Oh, that one. Oh, I don't know why that says 1.7. Sorry, that should say 1.3.
Okay, then
Then
should
yeah,
that
that changes. Yeah,
that changes everything? Which it was 5.8.
yeah. Sorry about that.
Yeah.
That's what I get for trying to rush. Yeah, I brought this 1.7 down to there.
Okay.
So
Okay.
thank you
Yeah.
for
'Cause
that.
I was just like I was like I'm
I
pretty
was good up until then, and you threw me. Yeah, yeah.
yeah. I was like I'm pretty sure something went wrong there. Okay.
Yeah.
Okay, makes sense because like I was trying to do it by myself. I was like, where did the 1.7 come from? Like, did he bring it from like the top or I don't know?
Yeah.
Okay. All right. All right. Thank you.
Sure, sure.
Have a good day.
You too.
Thank you.
You're welcome. You're welcome, Kay. Cade. Sorry. Brianna, anything you need before we wander off today? Okay. If something comes up, let me know.